So in this video, we will learn how to generate the coherent states, just like we saw how we generated the Fock states in the previous video. Before moving ahead, let me introduce different backends, or also called as numeric simulators, on the Strawberry Fields platform. So there are two types of numeric simulators provided by the Strawberry Fields platform. One is called the Gaussian backend, and other is called the Fock basis backend. Now, these two formulations are unique to the quantum's continuous variable model of quantum computation in the infinite Hilbert space. And the Gaussian backend, it provides state-of-the-art methods and functions for calculating fidelity and Fock state probabilities, involving calculations of the classically intractable Hafnian and so on. While on the other hand, the Fog backend, it allows operations such as squeezing and beam splitters to be performed in the Fock basis, that is the number basis. It is a computationally intensive calculation, and it can be done on the Fock backend. So this is the difference between the two backends. We can do different things on these different backends, and we should uh, mention them before simulating anything on the uh, Strawberry Fields platform. So now let us get back to the code. So just like in the previous video, we will now generate coherent state and plot the Wigner distribution function for the coherent states. So as usual, we will import the Strawberry Fields library and the operations library on the Strawberry Fields, which holds these gates, etc. Then we import the NumPy and also the matplotlib and the library for 3D plots. Then in the same way, we consider this one mode program, which is having only one mode. And now we generate the Fock state here, the vacuum state on the first mode, and then apply a displacement as such, where this 1 and zero point 0.5, it represents r and theta of the complex value alpha. So mod of alpha equal to 1, and e raised to I theta, where it's considered to be zero point 0.5. Now we run the code and then we plot it. Let's say, and this is the plot. So we consider this displacement by 1 on the from the vacuum state. So we can see that it is displaced a bit away from the center 0 0. So that is, it represents that it is a uh, coherent state. Let me try to change this a bit more, or let me change this to 1.5 and run it again. It is taking some time. Yeah, so we see that it has again displaced. The center of this distribution is displaced more again from the center 0 0. And now let's make it 4 and minus 4, let's say equal to 2, something like that. Let's see if it takes it a bit more away. Yes, you can see that it is getting displaced from its position. So this is the coherent state. We can change this value to rotate its position about the center, that is 0 0. Let's make it 2. Let's run it. You can see that it is rotated from the center. So this is the coherent state. We studied the coherent state and the Wigner distribution of the coherent state earlier, and here we have plotted it.